In this video, we're going to talk about what we can say about rhombuses that are more powerful than what we've already said about parallelograms. Like, like we had with rectangles in the last video, everything we knew about was true about everything we knew was true about parallelograms are going to be true of rhombuses because every rhombus is a parallelogram. But once again, rhombuses have that extra feature of all four sides being congruent, so there are probably some extra things we can say about them. In fact, this time, there are going to be two different things we can say about them. So we'll tackle the first one in this video. So I have just the diagram, and I kind of drew this rhombus by hand, and I drew in the diagonals, but I think you might be able to see something that's special about the diagonals that isn't true about an ordinary parallelogram's diagonals. They bisect each other. We knew that part, but that looks like a right angle. And if it's not a right angle, that might just be because I drew this rhombus by hand. But if I did this in GeoGebra, I could check and see that that actually was a right angle. So that's going to be a conjecture that we prove right here. So given that diagram, now, given that ABCD is a rhombus, we want to prove that the diagonals are perpendicular to each other. Okay, remember this symbol right here means the two line segments are perpendicular. And you can kind of see that it looks like these two lines that are part of the symbol are drawn at right angles. So hopefully that helps you remember that this talks about perpendicular sides. This one's a little harder to see. It uses some steps that we don't traditionally use. And so this time I'll use a T-chart. So if you try to do this, you might find yourself not getting very far or getting as far as you can. But here's the idea that I want to do. I want to talk about these angles here being right angles. So my plot for this is I want to talk about that yellow triangle and I want to talk about that pink triangle. So this is going to give me an opportunity. If I can show these two triangles are congruent to each other, which again isn't true of parallelograms in general, but is true of a rhombus, then maybe we can use that to talk about those angles right there. And maybe I should fill in that vertex where they intersect. All right, so we're going to start off with our givens. So ABCD is a rhombus. That's given. Okay, so looking at these two triangles, can you figure out as many reasons as you can to believe that that these two triangles would be congruent to each other? How much evidence can you see based on what we see? Some of them are harder than others. Some of them are easier than others. Well, one thing that pops right off at us, hopefully, is that common side. I hope you're recognizing whenever we see that common side that we're going to take advantage of saying that those two sides have to be congruent to each other because they're the same side. And that's the reflexive property. Another reason, go back and look at the definition of a rhombus, and that might give you a second piece of information. So a rhombus is a parallelogram with four congruent sides. So given that the four sides of this figure are congruent, we know that this side has got to be congruent to that side. So AD is congruent to DC. And that we're doing the definition of a rhombus. Okay, and the third piece of information, to have a hint, you want to look at all of the facts of parallelograms. One of these facts is going to help us define the third piece of evidence. Whoops. So for this, we're going to recognize that these two sides right here are part of the diagonal of this rhombus, which is a parallelogram, and we know the diagonals bisect each other. So we can say that AE is congruent to CE. And the reason for that is we're going to say diagonals of a parallelogram bisect each other. And math teachers might quibble about whether you can do that in one step or whether we should do multiple steps to do that. But if somebody is following your proof, you're doing just fine. So now we've got 3 congruence statements. I also want you to notice every time I come up with a congruent statement in a proof, I mark it in the diagram because that's going to help me when I need to get to the next step, which is where we are right now, of proving the 2 triangles are congruent. So ADE is congruent to CDE. And what's my reason for that? Once again, I'll cover up one of these triangles so you can just look at the evidence we've got for one triangle. So all we've got are sides. We've got 3 sides. So our reason for this is going to be the SSS theorem. Okay? Now, this is the part where the proof gets a little bit different from what we've done before, and I'm going to go ahead and say you're not going to be asked to do this in general. So if you can just follow along with my argument, you'll be just fine. So what I'm going to say is I can say that those two angles are congruent to each other. Because notice that when I take this triangle with this angle right here, and I flip it over to lie on top of the other triangle, the triangle that it's congruent to, the angle that I had marked here has now moved over to this spot. So these 2 angles have to be congruent to each other. So angle, I'm going to call these angle 1 and angle 2 just to make our lives a little easier, which I can do rather than calling them by their 3-letter name. I can say angle 1 is congruent to angle 2, and the reason for that is that those are corresponding parts of those congruent triangles. I proved that the triangles are congruent, so they're corresponding parts. All of the other angles must be congruent. CPCTC, corresponding parts of congruent triangles are congruent. All right, so that's an exciting thing. But we can also say angle 1 plus angle 2, or the measure of angle 1 plus the measure of angle 2, is equal to what? What do you get if you add these 2 degree measures together? You would get 180 degrees because they form a straight line. They're a linear pair. All right, and our reason for this, we haven't talked a ton about this, but we have talked about it a couple weeks ago. This is the additive property of angle measures. If we add the number of degrees in this angle to the number of degrees in this angle, we would get the number of degrees in the combined angle, which is a straight line. Remember, we did this when we proved that the sum of the angles in any triangle equal 180 degrees. So because these 2 angles are congruent and the sum of their angles equals 180 degrees, I can go ahead and say that the measure of angle 1 equals the measure of angle 2, which is equal to 90 degrees. And once again, I'm combining a few steps there. And IXL, when they do things like that, they just explain that saying that it's algebra. That's probably a little non-standard, but it doesn't matter. You are, like I say, you're not going to be asked to prove something quite like this. And if you do, you just do the best you can to explain what you're doing. So if two numbers are the same, and if they add up to 180 degrees, they both have to be 90-degree angles. And so because this angle and this angle are both 90 degrees, I can conclude that AC is perpendicular to BD. And can you imagine what I'm going to use to describe that? My reason for that is that that's going to be the definition of perpendicular. Perpendicular. So two lines are perpendicular if they form right angles where they meet. Okay, so what we just proved is that when you've got a rhombus, that the diagonals have to be perpendicular to each other. We're going to see in a future video that that's going to be a really important point for us to solve some problems. There are going to be some problems involving rhombuses and their diagonals, and we're going to be able to solve them knowing that they're perpendicular to each other. So look out for that. But first, we're going to prove the other thing that we're going to know is true about all rhombuses.